Hi everybody, Astral here again. I was going to shoot some stars tonight and take some pictures. And one thing you'll learn in astrophotography is weather is generally not your friend. Even though I thought today was going to be clear, based on what I checked 2 days ago, it is a fully cloudy night. I don't think you can see. I definitely can't see. But anyways, I wanted to talk to you more about the astrophotography subject and what you can do on these cloudy nights. On these cloudy nights, what most astrophotographers do is obviously they bring their gear inside, their rig, their scope, their mount, and they do processing on the images they took on the night before. We are generally nocturnal people who like to be night owls and stay up late. And these are cloudy nights. There's a good website called cloudynights.com where people go on and post a lot of experiences, what they're doing, troubleshooting, what they plan to do, and it's a good resource. And also I'd like to give a shout out to my buddy Rapton for really helping me jumpstart this channel and enlightening me that the fact is there's not much of a community for this astrophotography. And it's a very interesting, fun subject, and he recommended I put this on YouTube for you all. So that's what I'm doing. And anyways, the clouds, a problem. It's cold, can be a problem. But if you like the cold, this is for you for sure. Because cold nights, generally, let me rephrase this. The wintertime in the northern hemisphere is what's called nebula season. So the Milky Way arm, if you understand how the Milky Way is a spiral galaxy, the arm is usually directly overhead, and the nebula are located in that arm mainly. So the arm is full of gases, ionized gases, dark gases, a lot of hydrogen, oxygen, sulfur, and things that are your typical elements of the universe, and they make those beautiful gases that are called nebula that you take pictures of with your astrophotography setup. The interesting thing about that is the nebula, the red is generally hydrogen, and you use hydrogen alpha filters in monochrome cameras to capture those photons and really isolate and try and target that data. It's called data, like a data stream, kind of, when you're getting these photons from space. And the astrophotography, the ionized gases create these beautiful images in nebula because the gas is essentially electrified, lighting up basically. So you'll see a lot of these bright pictures of these nebulas. And there's also dark gases, and dark gases are not energized, and that means they are still there, and you can still see them because they can actually block out stars that are in the background, and they'll just be kind of like a blotchy blob of darkness with maybe a few stars in front of the gases, and it's blocking out the photons from getting through to your camera. And so you'll see these dark spots in nebula, and it's really interesting. I'm going to highlight that later in some of my other videos as I really start understanding what you want, how to compose myself for these videos, and generate a roadmap to demonstrate what I'm doing, how it's going to work in astrophotography, what you should start by doing. One of the big questions I've always had in astrophotography is, what is the good exposure time? What is a good exposure time? Everyone thinks that, okay, I see these images, I need to go for 300 seconds or as long as possible for these exposures. That's not necessarily true, and it depends on the equipment, the setup, and really what you're going for. So with the deep space objects and the nebula and these large star structures in space, such as the three pillars everyone may be aware of, another popular one, the Horsehead Nebula in Orion, and the Flame Nebula, the Eagle Nebula. You target these, and where was I going with this? You want the exposure to be if you're using a hyperstar or a focal reducer, you may speed up your exposure time, and you may experience, if you set your exposure time too high, you're getting way too much data, way too much light in your images, and it's going to be blown out. A lot of people do this with Andromeda for their first time, because Andromeda is a giant object, a structure in the sky as we call it, but obviously a galaxy, and it is beautiful when you image it. But the core of Andromeda will be blown out if you set your exposure too high. And maybe someone likes the blown out picture of the core, but it doesn't look as fancy, as nice as some of these NASA pictures you see, some of these other professionals and pictures. So you want to really, what I learned in astrophotography for exposure settings is you want to have the lowest possible exposure and the most amount of frames. Frames are the pictures, the fancy word for pictures, and I really think they should just call them pictures instead of frames. And what you'll learn is subframes are called subframes or light frames. They're really just the pictures you take. We're going to talk more about lights, darks, and flat frames. And lights are calibration frames, and darks are calibration frames, just to tell your telescope what the light is around it, so it can filter out just the general sense of the vignetting, essentially, a round image, a round circle around your images. If you don't do light frames, you'll see vignette. It's the best way to describe it. You'll have to look it up. I'll post some pictures and examples of what happens when you don't have flats. Darks are generally taken by covering the sensor of the camera to eliminate noise, electrical noise, essentially, on the chip itself. And if you don't do that, you will see literal noise. Like if you've ever held your camera in the darkness and turned it on and started recording, you don't see anything but just like these little blips of light from the noise sensor itself. And you can calibrate that out using dark frames, and algorithms predict and understand essentially what that noise looks like and what to take out of your photo without ruining your photo. So to recap, light frames are your pictures that you take. Dark frames are covered cameras that you take pictures of darkness, essentially. And the flat frames calibrate out vignetting and other anomalies that may occur. That sometimes you can see specks of dust when you do some of this light calibration that is in your telescope, lenses, glass, your filters. And there's a lot that can be captured by these super sensitive cameras that needs to be filtered out, but it can be filtered out. And a lot of people worry, like, oh, there's a satellite in my picture, and it's really cool when you see a satellite in your picture for the first time, but then it can become a headache if you don't understand what you're doing to filter it out. It'll just become a streak across your image. But if you use software like PixInsight and you use Blink, and you can see what frames have the satellite going across it, and you simply just delete the pictures. Like you're going to take up to some of my exposures with my Hyperstar and my 8-inch Celestron CST telescope. I will take these images, 150 images a night at 30 seconds each, and you use the process called Blink, which is a fancy way of saying just show me every image in at half a second. So it looks like a really jerky video going really fast of your telescope and what it saw that night. You took all those frames, and you can pause it and delete those photos and just that have artifacts, bugs that fly across. I've had that happen one time. A moth got too close and it looked like it might have caused some issues. Helicopters, planes, even some clouds might drift in your images every now and then. You see it and you just delete it, and then you can adequately stack, what's called stacking your photos. I'll get to that process. That's post-processing in order to formulate your final image. So you have 150 of these pictures, and I guess I should start there and explain what you're doing with these pictures. When you have 150 pictures, how do you make that into your final image? You literally stack them all together at one time, and software will look at each star in the picture, line them up, and put them on top of each other. Every picture you have will be slightly different in the movement region. Like the telescope's still going to have micro movements, and you'll see it when you start your first blink. You need careful guiding and a careful polar alignment in order to minimize the movement of the telescope, but it'll settle and it'll adjust every time prior to taking the picture. Each picture every 30 seconds, depending on your settings, and it will calibrate that for you. So there's a lot to learn in this, but don't be overwhelmed by it. So you stack all these pictures together. The computer targets each star and kind of connects the dots. And then it brings out all of the data that was gathered, because you're essentially putting as much, the photons are collected and they're dim in each light frame that you take. But all together, it really starts to light up when they are stacked or smashed together, and creates a great image for your deep space nebula. Because remember, they're faint objects. You can't even see them with your naked eye. The fact is, even in these light pollution zones, a lot of people say, I can't take astrophotography pictures because I'm in a Bortle 10 and it's just light pollution everywhere, like the Phoenix or Las Vegas or just New York City. That's incorrect. You can do it. You filter out a lot of the light pollution using an L-enhanced filter or some other types of filters. You ideally do want to be in the darkest area, Bortle 1 zone period, and have excellent seeing, and your stars in the background of your images will just pop. They'll look great. But yes, you can still absolutely get stunning photographs in cityscapes, and I was worried about this myself when I first started this hobby. So another thing, it's kind of a good thing that in nebula season, I was saying earlier, in the winter in the northern hemisphere, the heat in the summer can cause heat waves and turbulence and issues in the atmosphere that can and will be detected and screw up your images. And the Milky Way arm during the summer seasons in the northern hemisphere, it's not as visible. Like it's lower on the horizon. So ideally, 30 degrees up from the horizon is the minimum you need to be pointing your telescope in order to get these objects. Once objects, stars, planets get too close to the horizon, you're not going to be able to image them well without atmospheric disturbances, low seeing quality, and general noise from Earth. I mean, pollution gathers, especially in the first 10 degrees off the horizon. You're going to get tons of pollution, and I could use some fancy words here to describe how light, bounces off that. But generally speaking, keep it above 30 degrees off the horizon when you're imaging, and you'll have less problems. Ideally, you want to be as overhead as possible, and there's some issues with that in terms of guiding, but we'll talk about that later. I've ironed that out really quickly, but yeah. In the summer season, it's the planetary season, and it's a lot of people like to take pictures of the planets, and we'll describe that. It's actually not pictures, it's videos. You're going to record videos and stack the videos together. But the summer season, you're not going to get much nebula because the Milky Way arm that we are in is too close to the horizon. You may be able to get some images, but yeah, when it's colder out in the wintertime, there's less disturbances in the atmosphere, less heat, no heat waves. And it's going to be cold for you, and it's going to be cold on your telescope, which is a good thing for the camera, and something you deal with the telescope, because the temperature changes and causes flexing, which causes the lens, the mirrors to shift a tiny bit, but enough to not defocus your stars, but cause your stars to look, maybe have a halo effect or other issues. So what you do with your telescope in those instances is you're going to leave it outside and make sure it's not going to rain that day and that night. And then you leave it outside to kind of as early as possible. I put my telescope out around 5 p.m. Sometimes I'll leave it out all day and all night and for a week at a time, very carefully, because you don't want to forget it. If it rains, you're screwed. You just ruined a lot of equipment potentially. Maybe not. You might get lucky. So don't worry too much. Don't immediately turn it on if anything gets wet. Let it dry. Use the rice trick. And I've never had this happen, so I haven't had to do it. I can't speak for this, but you leave your telescope out during these colder temperatures so it adjusts. And so by the time you're ready to shoot that night, it's not coming from your warm living room or warm garage and then stuck immediately in the cold for it to just, it's aluminum, cool metal fast and have a lot of flexing. And this sounds intimidating, like, oh God, am I breaking my telescope? Is it out of calibration? No, the tubes, it's going to be fine. It just, like I said, it shifts. So we'll talk about collimation and the effects of that later on in this channel. And that's actually a struggle I'm going through right now with my Hyperstar, which you can do it and you can learn how to collimate. But collimation is basically the accuracy of the lens alignment with the mirrors and the positioning of them. You just turn some screws and make them realign, basically, so your stars look nice and round. And you want that, it's called eccentricity of the stars, the nice roundness of the stars. And another thing I want to talk about too with that, a lot of people who use I'm using the SCT telescope. Refractor telescopes cause something called diffraction spikes in stars, and some people really like those. And those are the stars that will look like a cross, like with an X and E. You'll see like lines coming off the stars, and it looks like your typical stereotype of a star. But stars, the sun doesn't have diffraction spikes. It's round. Stars are round. And the SCT telescopes, Schmidt-Cassegrains, don't have that issue, and a lot of people don't like diffraction spikes because it's less natural, and they want to see an image of space. They want it to be as natural and close to real as possible. It's next to impossible to get an accurate, perfectly accurate color, I guess you could say palette of space, nebula, etc., because you've got the red shift going on from the light traveling so far. You've got so many different aspects. Your computer's calibration, and when you put it on a screen, your monitor, everyone's monitor is going to be slightly different in how it displays colors. Even the same model of a monitor, the exact same monitor off the same assembly line might be different. And there's certain monitors you can get that have certifications that get them as close as possible to true color intended for the user's eye and perception. But there's a whole physics and things I don't understand about how this works in optics. But I mean, I read the other day that basically people all may perceive colors slightly differently just based on the cones in their eyes. And I mean, I even saw a nice video the other day where there's a possibility that our ancestors never saw the color blue, like hundreds of years ago when it was first being documented. People did not see the color blue, and they wrote about the sky as being just like either a dark gray or a light black, and maybe a greenish tint to it. And it was a study done on some tribes where they took a picture of a color wheel of all greens and put one blue in there. So they had like 11 green squares and one blue square. And they said, what color are all these? Find the one different square. And this tribe in a remote area was unable to point out the blue square. It's mind-blowing. Like that's a thing. So people talk colors. If you get picky about colors and want to know the true color of space, never worry about that, because in all honesty, the color is, you get it as close as possible, obviously, but there's people who nitpick about getting the color as true as possible. You'll realize what I'm talking about, especially in the post-processing of these nebula. You're going to adjust the vibrance, the contrasts, the brightness, and the basically setting of the reds, blues, and greens. And they're going to be different each time. And you're going to realize, oh, well, I don't actually know what space looks like, because you can't just go outside and look up and see for yourself and say, oh, that's what the red was supposed to look like, and mine is this or that. And so the Hubble palette is generally a false color palette of images designed to make, deep space objects look really cool. However, it's using false colors. I mean, we'll expand on that later too. But anyways, I wanted to keep this video a little short. I know I'm rambling. I'm getting used to streaming. I'm getting used to doing a channel. I need your input. Am I going down too many rabbit holes? Am I a squirrel bouncing all over the place, with too many subjects at once? I'm going to focus this down and make videos, step-by-step videos for each topic as much as possible. But it's hard for me to describe astrophotography without just crashing into random topics all at once. Like, maybe someone could do it. I am someone who kind of goes all over the place. Help me out, and thank you for watching again. So if you want, like, subscribe, keep following me, and I'll keep making content. My content will get better. I promise that. My roadmap will get better. So thanks for watching. Have a good night and clear skies, everybody.